So we've determined how to find the permutations of 4 different objects. If I have 4 different letters, these are all the permutations of those 4 letters. And I know I can get that by just doing 4 factorial is 24. What I want to look at now is what if what if some of the objects were the same? Alright, so down below here, what I'm going to do is I'm going to change all of the F's to E's so that I have 4 letters, A, B, E, E, but 2 of the letters are the same, as you can see. So if I make that change in my list, it's going to go down. Just going to go and do all this. And if you take a close look at your letters now, you're going to notice that I'm going to have fewer permutations because I'm going to have repeats in my lists. Specifically, all of these permutations are the same as these. So I don't need to count these again. All of these are the same as these, so I don't need to count these. And similarly here, these are the same as these. And so I don't have 24 permutations anymore, I have half that number. I have 12. How does this compare? It's half of the 4 factorial. So we're looking for how does the original number of permutations change when I have identical objects. If I have 2 identical objects, it's half. What happens when I have 3 identical objects? So what I'm going to do in the list now, my original list, is change all the F's, B's to F's and E's to B's, so that I have 4 letters, but 3 of them are B's and 1 of them is an A. All right. So I'm going to go through and do that. I'm going to go across ways this time. So A, B, this will be B, B. This will be A, B, B, B. That's the same as the first. This will be A, B, B, B. That's the same as the first 3. And it's turning out that, in fact, the entire first row are all the same. This is all the same permutation. So that's 1 permutation, not 6. Okay? And if I do the same in the other rows, these are all going to be the same. And so are these. And so are these. And so I can see that I have 4 permutations, not 24. And I can see that with 3 objects, my number is 1/6 of what it was before. Now 1/6 I can think of as 1 over 3 factorial. 2 objects, the number of choices was reduced by a half, which is the same as 1 over 2 factorial. If I have 3 identical objects, my list is reduced by 1 over 3 factorial. It's reduced by 1/6. Alright, to get 4. So I think you can see where we're going with this. The number of permutations of n objects, if they're all different, that's n factorial. But if we have some of them that are alike, if we have A objects that are alike, we know that we have to divide that by A factorial. We can hopefully see that in the 2 examples above. And actually you can extend this, because if you had A objects of one kind and B objects of another kind and C objects of another kind and so on, you would just divide by those to get the number of permutations. So how many permutations are there of the letters in the word Ogopogo? Well, we know that if these were all different letters, we have 7 letters, so that would be 7 factorial. But we have 4 O's, 2 G's, and everything else is different. So our total number of permutations of these letters would be 7 factorial divided by 4 factorial times 2 factorial. So 7 factorial divided by 4 factorial I know is 24 times 2 factorial I know is 2. So 105 different permutations. Alright, here's another example. We have a true and false test which has 7 questions. And you're going to answer each question true or false. So for example, I could answer the test. Question 1 I could answer true. Question 2 false. Question 3 false. Question 4 true, etc. Okay, there's one way I could answer the 7 questions. The question is, how many different ways could I answer the test? Or if the teacher was doing this, how many different answer keys would be possible if we had 3 trues and 4 falses, which is what I've just drawn here. Okay, so if I had a different response for all 7 questions, that would be 7 factorial, but I'm going to have an identical response because I'm going to have 4 falses and 3 trues. So 7 factorial divided by 4 factorial is 24 and 3 factorial is 6. So 35 different answer keys. Okay, last example, we want to know how many ways are there to get from point A to point B. So we could, go 2 right and 4 down. And I'm going to express this as, I basically got 6 movements I need to make. I can do 2 rights and 4 downs. And we're only allowed to travel right and down, east and south, as it says. I could go down and right and down and down and right and down. That would be another way to get there. Down, right, down, down, right, down. But you can see that this question is really a permutation question with identical objects, because I basically have to make 6 movements, but 2 of the movements are going to be right, so those are identical, and 4 of the movements are going to be down. And so I can work that out. 6 factorial divided by 2 factorial it was, which is 2, times 4 factorial, which is 24. So there's 15 different ways I can get from point A to B. Alright, now what we're going to look at are some more complex situations involving permutations. In this example we have a French poster, 2 math posters, and 3 science posters, which we want to organize or place on a wall in a row. But we have a constraint involved here, and that is that the 2 math posters need to be together on an end. So either together there or together there. Alright, let's just start by thinking about them together at the front, in which case our 4 other posters would be there. And so when you've got a situation in which you have a constraint happening, you have to consider each of the situations separately and then combine them with the fundamental counting principle. Here's what I mean. Your 2 math posters, if you just think of those, there's 2 factorial ways of organizing them, right? 2 different posters, 2 factorial ways. For just the other posters, there are 4 factorial ways of organizing those. So for each of the 2 factorial ways to arrange the math posters, I'm going to multiply by the fundamental counting principle the 4 factorial ways to organize the other posters. Alright? But there is one more thing involved here, and that is the fact that we kind of have 2 groupings. And so these 2 units could be swapped as well. In other words, there's 2 factorial ways to organize the units, because the math posters could go at the back. So I need to multiply by another 2 factorial and work all that out. And that's going to be 96 different ways to organize the posters. Here's another situation. The same 6 posters, but this time we want the 3 science posters to be together. So they could be at the front, let's say, Science 1, Science 2, Science 3. But the position of this unit could also swap around with these other posters. So the constraint is that the three science posters must be together. So there's 3 factorial ways to just organize those within the unit. But then there are 4 individual units that can be moved around. So for each of the 3 factorial ways to arrange the science posters, there are 4 factorial ways to organize the units. This is the fundamental counting principle. I'm multiplying the sections. So that's 24 times 6, 144 different ways. And one more question with our posters. What if our 3 science posters could not all be together? How many ways are there of organizing the posters that way? Well, we know that there's 144 ways in which the 3 science posters must be together. We also know that there are 6 factorial total arrangements if we don't care where any of the posters are. So then, if we take our total arrangements minus the number of arrangements in which the science posters are all together, that should be the number of ways in which the 3 science posters are not all together. And so that's 720 minus 144, 576. One last example to look at. We would like to know how many 4-digit odd numbers we can make using the digits 1 to 7 if the numbers that we're creating are less than 6,000. So a 4-digit number, which must be odd, and so we know that the numbers that are allowable here are 1, 3, 5, and 7. The numbers that are allowable at the front, since the number must be less than 5,000, are 1, 2, 3, 4, and 5, and any of the leftover numbers can go in the middle positions. Now, the extra complicating factor here is that determining the number of permutations will depend on where the numbers 1, 3, and 5 appear. Because if they appear here, they won't be able to appear here. Alright? So this is a situation in which we have to look at separate cases. Case 1 is going to be when the units digit, that's this one here, is a 1, a 3, or a 5. Alright? In other words, there are 3 possibilities for the final position. If we have a 1, 3, or 5 in the units digit, we can't have a 1, 3, or 5 here, which would leave us with 4 possibilities for the front. And we now have 5 digits left over, and so we have to pick 2 of those 5 digits to fill these positions. And the order here would matter. So for these 2 spaces together, there are 5 pick 2 ways to choose those. So the number of permutations, assuming digits of 1, 3, and 5 in the unit spot, 4 times 5 pick 2, 5 permutations of 2 times 3. I often use the word pick for permutations. The order matters. And if you work that out, there are 240 permutations. But the other case is if our units digit is a 7. In that case, there's only one way to pick this number, and that means that any of the other 5 numbers can be used at the front, leaving us 5 numbers, and we need to pick 2 for the middle 2 positions. And if we work that out, we get 100 permutations, and so the total number of ways to create these numbers is the sum of these two, 340 different numbers.